Hello, this is Joel Connis's tutorial for video solution. So starting off, we're tasked to find this transfer function theta L on EA. So EA is this voltage here, and theta L is this angle at the load. Okay, here are the values that we're working with. This just makes sure that the notation makes sense and we can understand what the values are. Then I use this relationship to find what our equivalent loads are, impedances, and angles. This is related to the next diagram I have to show you, which is this here. This is the reflection at the gear teeth, and it also is the schematic in the Laplace domain. So that's really handy because what we're going to do next is break this diagram up into our two bodies. So when we move this torque this way, what we expect is to get a resistance from the body's inertia and from the spring K1 when it's related to this angle. And then we should also pick up some other patterns, which is if we're looking at this angle in terms of K1, it should be heading, the arrows should be heading into each other. And then if we look at K1 on the other side, this arrow will head into this arrow. That's what we would expect. And also our final litmus test is that this arrow with this angle, theta L, heads into this one. So also this arrow here goes against that one. That's because this is a shared component. And so that makes sense. Let's go ahead and build our equations of motion. The first body is put in static equilibrium, and therefore the sum of the forces equals to 0. Then by following this sign convention, we can organize the equation like this. Following up, we can then sub in these values for our equivalences at the gearbox, and we find our first equation. In a similar vein, we do the same thing for the second body and make this substitution here. And now we have our second equation. Before moving on, let's look at our problem. There are two equations with three unknowns. We don't know the torque at the motor, theta L, or theta M. But by substituting equation 2 into equation 1, we can get a relationship between torque at the motor and the angle at the motor, as shown here in equation 3. This is useful because the motor torque is related to the motor angle once we do our circuit analysis. This is going to even out our unknowns and it will make the problem solvable. Now let's focus on the circuit analysis. We take the schematic from the problem statement and we move it into the Laplace domain. Then we use this relationship combined with Kirchhoff's voltage law around the loop IA, and we find equation 4. This step is really important. Equation 4 brings in this term which we need for our transfer function, EA, and it also removes Tm by substitution. And it now leaves everything in terms of theta M, which was our other unknown. Importantly, theta M can be rearranged so that it's in relation to theta L. This is the other unknown for our transfer function. Finally, theta M can be removed from our equation by substitution. What we're left with is a relationship with two variables which are needed for our transfer function. Notice that by dividing theta L across to each side, we have a transfer function, just not the one we want. To proceed, we're going to substitute the values that were given in the problem statement, expand and simplify, then make the function go to the standard form by dividing by 0.0024, and then rearrange for theta L on EA, because currently this is not the correct form for our transfer function. This is the transfer function. Thanks for watching.